Hello everyone, my name is Ahmed Mostafa, and today I'm gonna be talking about my final submission for the subject ELCN 100, a laboratory subject which is supervised by Dr. Hassan Mostafa. And for my final project I chose to design the spectrum analyzer. Briefly speaking, the spectrum analyzer is a measurement device which displays a certain wave or a certain signal on the frequency domain rather than the time domain that we're always used to seeing. Therefore, at a certain frequency, which is the fundamental frequency, there displays a component, and if there are other harmonics, it is displayed in multiples of this frequency. If you could just run this program now. Here we can set the amplitude. Let's set it at 5, and then the frequency, let's set it at, for example, 50. We can see that for a sine wave, there is a single component at 50, which is what we expected, as the sine wave only has one component at the fundamental frequency. However, if we change the wave type to sawtooth, for example, we could see that at certain multiples of the frequency, like 100 and 150, etc., there are smaller but other harmonics. Also, we can add some noise to the signal. Let's add, for example, a noise of 5. Here we can see the noise, it's acting up on the signal, therefore it changes the readings a bit. Let's put it back to 0. Here we could change the scaling to dB, which is decibels, and as we know, there are negative values, as decibel is for the y-axis is the 10 log of base 10 of y, so it displays negative values for values that are under 1. Now and here is the phase slider. For the phase, we could adjust the phase of the signal if you want to, and here is the window. Briefly speaking, also the window is an optimization for the time domain, and if we don't actually know that exactly what we're doing with the window, we should just leave it at panning, as this works best with most signals. Here are the averaging parameters. We could choose no averaging, or we could choose to average by using the peak hold or the RMS averaging, etc. We could use the weighting mode, which is exponential or linear, and the number of averages, which is how many readings of for example 1 second do we take before the graph settles and averages on this number of readings. Now moving on to the block diagram. This is the diagram for the device. Here we have an enum which is connected to the case selector. The case selector has the type of signal that we're going to display. The first case is a sine, and then the second, let me stop it, yes. The second is a triangle, and then the third is a square. The fourth is a sawtooth. Here are two dials for the amplitude and the frequency respectively, and then there is a phase slider, horizontal slider, which we showcased in the front panel. Here is a dial for the noise. And this is the uniform waveform generator which we used as the noise in this experiment. We could get it from right click, signal processing, waveform generation. Here is the uniform, and here are the type of waves, sine, square, etc. We take the output of the wave generation accompanied with the noise, we add them together, and then we display them on the generated function, which displays the function without any transformations. And then we take it and add it to the FFT, which is the fast Fourier transform. This output is then connected to the spectrum analyzer graph, which plots it as we saw on the front panel. Here we added some controls, which is the dB on, which makes us display the values in decibels, and the window, which also we covered in the front panel. And here are the averaging parameters. In order to run this device continuously, we added a while loop, which you could go right click and structures and while loop, and then we encased all of these circuit in the while loop, and then we added a stop button in order to be a stopping condition for this loop. That's all for my LabView project. Thank you for listening.